Let's demystify the buffer solution. A buffer solution is a special case equilibrium that resists pH change. Now, with some calculations, I'm going to show you how it resists that pH change, or how much it resists that pH change. Typically, when we define a buffer, we define it as being comprised, it's a solution comprised of a weak acid and that weak acid's conjugate base. They have to be related. So oftentimes we will say any weak acid is HA and its conjugate base is then A-. This part, without an H, is the conjugate base. Now, fundamentally, we can also say it's a weak base and the conjugate acid of that base. But to keep things simple, we're going to start with a weak acid and its conjugate base. Now, we know from previous chapter or module that when we have a weak acid, it's in equilibrium with its dissociated contents. So that means you have your weak acid HA in an equilibrium with its parts, H+ and A-. We also know from a previous module that if we change the concentration of any one of these parts, the equilibrium will shift in order to restabilize or re-equilibrate. So if I increase the concentration of HA, then the equilibrium will shift towards the production of products. So if I increase the concentration of HA, I must be adding to this side. If I decrease the concentration of any one of my parts, so let's say I decrease the concentration of my H+, I will also be shifting towards the production of products, so I will be adding to this side, in order to re-establish that equilibrium. Now, if you take all of this away, then our equilibrium is going to shift this way. So we know that from the equilibrium chapter, how the equilibrium will behave. So now let's put it into context of the buffers. Let's calculate the pH of a buffer solution that has initial concentrations of both the acid and the conjugate base. Now, for this particular example, I'm going to be using benzoic acid. You don't have to know what benzoic acid is to be able to look it up on the table, because typically you're going to have the name. That means the conjugate base is going to be sodium, I was going to spell sodium Na. So sodium benzoate. Now, the chemical formula for this, if you're interested, is NaC7H5O2. So this part is the benzoate. That means the benzoic acid is going to look like this. Now, remember, for an acid, we oftentimes put the H to the left, or the acidic hydrogens go on the left if there's more than one. But benzoic acid will dissociate like this. And we have initial concentrations. So this buffer solution has an initial concentration, or our buffer solution has 0.050 capital M molar benzoic acid, and it has 0.150 molar sodium benzoate. Now remember that capital M molar is moles of solute divided by liters of solution. Now, this buffer is going to change. It's going to change somehow in order to create an equilibrium. How do I know where to add and where to subtract? Well, notice that we do have an initial concentration of our acid. We have an initial concentration of our conjugate base, but we have no initial concentration of hydrogen ion. So because we can't take anything away if we don't have it, we must be adding to the product side. That means we're taking away from the reactant side. So at equilibrium, these are our concentrations, and you've seen this before with our weak acid chapter. The difference is we now have an initial concentration here. Now the Ka for benzoic acid, and most of the time the Kas would be given to you. It's possible that you would have to look it up in the table in the classroom, but I'm going to give you this one. So just double checking my little 5, 6.5 times 10 to the negative 5 is going to be equal to the concentration of the products at equilibrium multiplied together divided by the concentration of the reactants at equilibrium multiplied together. So I fill in my values like this. That equals 6.5 times 10 to the negative 5. And now I can solve. So this looks kind of hairy because we do have both a plus here and a minus here. What am I going to do? Well, remember your rule of 1,000. If your initial concentrations are more than 1,000 times greater than your Ka value, you can simplify. Now, we are right on the edge here, and really, by definition, I'm not sure I'd be comfortable with that, but look, this one is more. So we're going to simplify. We're going to try it and see how it goes. So I'm going to simplify this, which means these x's go away. Now, we can simplify because that 1,000 times rule, the change is going to be so small compared to the initial concentrations. That's why we can simplify. So then I'm going to go through these steps, x times 0.150 over 0.050, and that's going to be equal to my Ka value, 6.5 times 10 to the negative 5. And now we're going to need to calculate. Now, just briefly, the algebra for this, we multiply both sides by the denominator. So 6.5 times 10 to the negative 5 times 0.05. You should get 3.25 times 10 to the negative 6 for that. And now divide both sides by 0.15. And you get an x value of 2.1. It's actually 2.1 and 6 repeating. I'm going to round that up to 7. Times 10 to the negative 5. Now, the unit for that is capital M molar. But what does x represent here? Well, x represents the change. It also happens to be the concentration of my hydrogen ion. So if I'm calculating the pH of this buffer solution, remember pH equals the negative log log of the concentration of the hydrogen ion, then I'm going to take the log of this value, and I get 4.6, I actually get 664, so we'll call it 4.66. Now for buffers, we also have a shortcut equation. That shortcut equation is called the Henderson-Hasselbach Equation. So if you analyze the K value and the initial values and you think, I'm probably going to be able to simplify that, you can use this Henderson-Hasselbach equation, which is the pH is equal to the pKa plus the log of the ratio of the conjugate base over the weak acid. Now remember, the pKa is the negative log value of the Ka. So the pKa for this acid, I calculate that to be 4.19. And I'm going to add that to the log of this ratio, A minus to HA. Now, I purposely did not put the square brackets here, and I did not put the square brackets here because we can use moles there. So I'm just going to leave it as the ratio. It needs to be molarity or moles. The molarities were given to us in the problem, so this can work out very quickly to have 4.1 plus the log log of the initial concentrations because we can simplify. So 0.150 over 0.050. So work that in your calculator. Make sure you have put it in your calculator correctly. I'll put the, I'll do it this way. Give you the little pieces. And then I get a pH is equal to 4 and I get 6.6, and then 7 is my next term. See this hundredths place here? I'm not concerned about that. That just does not faze me in the least, and you would get credit for either one of these answers. It's the same numbers, and it's just working with them slightly differently. So when you can simplify a buffer equation, you can use the Henderson-Hasselbach equation. So let's work another one. Now, commonly when you find example problems for buffers in a general chemistry class, they commonly use acetic acid. And the reason they use acetic acid is because it's vinegar, or vinegar is acetic acid. And therefore, many book writers and people who are producing these practice questions and such, they think it's approachable because many people know what vinegar is. So let's just look at an acetic acid solution. We'll just review a little bit. So if we have acetic acid, now acetic acid is HC2H3O2, and we're going to just, put it in water. So this is our weak acid. We just have this weak acid hanging around. And we're going to have a solution, and it's going to be 50 milliliters of a 0.10 capital M molar acetic acid solution. Now the Ka for acetic acid is 1.8 times 10 to the negative 5. You're going to use acetic acid a lot. You might as well memorize that or at least write it down on your note sheet. So if we just have this solution, what is the pH? Now this throws back to our weak acid chapter. Well, we have our initial concentration here. It doesn't matter how much we have. This is our initial. And initially we have 0 of our products. And we will change this concentration by some value X that I don't know yet. And then at equilibrium, these are our concentrations. Now, analyzing the Ka, we're 10 to the minus 5, we're 0.1. That means we can simplify. So that's going to mean we have 1.8 times 10 to the negative 5 is going to be equal to, I'll write it out loud first, why not? Then we simplify, and then we multiply both sides by 0.1. And then, so 1.8 times 10 to the negative 6 equals x squared. Take the square root of both sides. And I get 1.34 times 10 to the negative 3, capital M, capital M molar. This X represents the concentration of the hydrogen ion. That means the pH of this solution is 2.88. Now, what happens when we take this solution, let's see, rather than erase, let's move over. Now we're going to take our weak acid, so our acetic acid, and we're going to react it with a strong base. This time, this strong base, we're going to put 10 milliliters of a 0.10 capital M molar sodium hydroxide solution. Remember, sodium hydroxide is a strong base. It completely dissociates. So whatever I have of sodium hydroxide, I have of hydroxide. So I have 50 milliliters of my acetic acid, and that acetic acid had a molarity of 0.10 molar. But how do I know how much is reacting here? Well, remember from stoichiometry chemistry 1 that 1 mole, because I have a 1 here, remember the absence of a number is a 1, or this is our balanced chemical equation, we react our moles. So 1 mole of our weak acid reacts with 1 mole of our strong base. And that produces 1 mole of water and 1 mole of our conjugate base. So we need to figure out how many moles we have to figure out what's reacting. So I'm going to take my volume. I'm going to work with the weak acid first. So I'm going to take the volume and I convert that into liters, and I'm going to multiply that by the molarity, so moles per liter. So my liters cancel out, and then I get 0.005. We're going to hold on to significant figures, and I'm going to leave it there. I know that's one significant digit, but I think this is going to get hairy enough. So this is moles of acid to begin with. Then I'm going to work with my strong base. So my strong base, I start with my volume, multiply it by the concentration. Liters cancel out, and I get 0.001. Again, I know that's one significant digit. Bear with me here. Moles of base. Now I know that this reacts 1-to-1. It is a complete reaction. We have a single-headed arrow. It does not come back in an equilibrium. So the weak acid reacts with the strong base and it just goes away. In order for it to go away, mathematically, we subtract. So we subtract the moles of the base from the moles of the acid. So when I use these moles of base, then what I'm doing is I'm making 0.001 moles of my conjugate base. When these two react, however, I have 0.004 moles of my acid left. There are no moles of my hydroxide left because they have converted into my conjugate base. Now, what are the concentrations here? Now we're going to treat it as a buffer. So now that my weak acid has reacted with my strong base, now I'm going to form a buffer reaction. So I have 0.004 moles of my acid left. What is the concentration? Well, I have to divide those moles by the total volume. So I had 50 milliliters of acid and 10 milliliters of base. I will be dividing this by 0.060 because that is 60 milliliters as a liter. So my initial concentration then for this buffer solution is 0.06, and then I have a 6 repeating. So I'll do it like that. Now for my conjugate base, I take that 0.001 moles and divide it by 60 milliliters, and I get a concentration of 0.016, and then the 6 repeats. So I'm just going to drop it like that. So then we have our molarity. We are going to change by some amount, x. Which side gets the minus and which side gets the plus? Well, when we reacted up here, when we reacted this hydroxide, we made water. We took that H away. There is no H initially. So we will be adding to the product side and taking away from the reactant side. So at equilibrium, we have these values. So now we can write the Ka expression and solve for x. So our Ka is 1.8 times 10 to the negative 5. And look at that. We are really close to being able to simplify. I'm thinking we should try. So let's try to simplify. We can always use the 5% rule and double check. So I'm going to take my 1.8 times 10 to the negative 5, and I'm going to multiply it by 0.0667. And I get 1.2006. I'm leaving this in my calculator. That's why I'm going to give you all of the digits times 10 to the negative 6. And that equals 0.016, drop the 7, x. Divide both sides by 0.0167. And I get an x value is equal to 7.189 times 10 to the negative 5th. Now, what does that x represent? In this case, that x represents the concentration of the hydrogen ion. So to find the pH is the negative log log of that concentration, so 7.189 times 10 to the negative 5th. And I get a pH value of 4.14. So let's just double check. Let's use that 5% rule and see if simplifying was okay. And in order to use that 5% rule, what I do is I take my x value, 7.189 times 10 to the negative 5th, and I divide it by the smaller of my initial concentrations. So I'm going to call that 0.0167 to find out if this was a valid assumption to make. Divided by 0.167. Multiply it by 100, and I actually get 0.4. So it was definitely a valid assumption. We can definitely simplify that. Now, because we can simplify that, and this is a buffer, let's use the Henderson-Hasselbach, and let's see if we get the same answer. pH is equal to pKa plus the log, the concentration of the conjugate base and the weak acid. But this time, instead of going through this stuff with the concentrations, I'm going to use these moles. So this was the weak or the conjugate base, And then this one, moles of acid. Let's just see what happens here. So the pKa is 4.74. Remember, to find the pKa, you take the log, the log of the Ka value, 1.8 times 10 to the negative fifth, drop the negative sign. So 4.74 plus the log of the ratio of the conjugate base, 0.001, over the weak acid, 0.004. So doing that quick, well, I should probably do this stepwise as well. Plus. So 0.001 divided by 0.004. And I get 4.1379, so that would round to 4.14. So you see we can use the Henderson-Hasselbach and get the same value. So then what happens, or what are the calculations? Let's say, let me see, I had 50 milliliters, 0.1. Well, what if I have, if I start with 50 milliliters of my 0.10 molar acetic acid, just as before, and this time I'm going to add 25 milliliters of my strong base. My strong base is going to have the same concentration. Well, as before, we need to react moles to moles. So for every 1 mole of acid, we're going to react 1 mole of our strong base. So like a limiting reactant, what I'm doing is figuring out how many moles I have. So I'm going to start with 0.050 liters of my acid, multiply that by my concentration in order to find out how many moles of acid I have. So I have the same as before. Again, I'm just going to try to truncate. So this is moles of HA. And that is reacting with 0.25 liters, 10 mole. Oops, not 0.01, 0.1. So I have 0.0025 moles of base. Because it reacts 1 to 1 in order to form water and my conjugate base, I'm just going to subtract because the hydroxide here is my limiting reactant. You can look at it that way. So 0.005 minus 0.0025, then we have 0.0025 moles of HA left. Now, this is a single-headed arrow. That means it goes one way. So I am producing, with these reactants, I produce 0.0025 moles of conjugate base. Now, this water is a liquid, and remember, the water as a liquid does not go in our Ka expression. So we form this buffer solution. So we have our weak acid, and it dissociates into our hydrogen ion and our conjugate base. The Ka for this is still 1.8 times 10 to the negative 5. So we're still pretty close here with our moles. I'm just going to use the Henderson-Hasselbach. pH equals pKa plus the log of the concentration, or the ratio of the moles of conjugate base to weak acid. So the pKa is 4.74, and the A minus now is 0.0025, and the HA is what is left, also 0.0025. Now the log of 1 is 0. So this is where the pH equals the pKa, which is 4.74. This is a special case called the half equivalence point. And you can actually find this on a graph when you do a titration. We don't do that in my Barton course. So if you're watching this for my Barton course, that's just a little brain candy for you. But what happens if we go past, or let's go to the equivalence point and then we'll go past the equivalence point. So we have our HA, and we have 50 milliliters of it, 0.1 molar. And now we're going to react it stoichiometrically. That means we're going to add exactly the same number of moles of O minus. So we have 0.005 moles of our acid, and we're going to react it with 0.005 moles of our strong base. Well, what's going to happen is we're going to make water and 0.005 moles of our A minus. So now the reaction is no longer dependent on HA and Ka. It's only dependent on what's happening over here with this conjugate base. So now we have to flip the equation around. So now I have my A minus, which is going to be reacting with water and form an equilibrium. And that equilibrium will have this is now considered a base. This is called the conjugate acid, where we take the base and add an H, and then the conjugate base of water, which is OH minus. So now we've started with 0.005 moles of our conjugate base, but we don't have anything else to shift. So we do need to make that into molarity. So we have to divide this by our total volume. Our total volume is 100 milliliters. So we take our moles, 0.005, and divide that by 0.1. So our initial concentration of A minus is 0.05 capital M molar. And we have no HA and no O minus, or excuse me, hydroxide, OH minus, because we stoichiometrically reacted them. So now we need to change this. We're going to take away some of our A minus and we're going to make HA and OH. So at equilibrium, we have 0.05 minus X, X, and X. But we are no longer dependent on the Ka. We are dependent on the Kb. Now, Kb can be found by dividing Kw by Ka, because Kw is going to be equal to Ka times Kb. So because we have our Ka and Kw is known, 1.0 times 10 to the negative 14th, and our Ka was 1.8 times 10 to the negative 5, then we can calculate that Kb. Make sure you put it in your calculator correctly. Use your EE function or your exponent function. 5.5, and then my 5 repeats. I'm going to call it 5.56 times 10 to the negative 10. That is the Kb for this particular acid. And that's what we have here is the Kb expression. So 5.56 times 10 to the negative 10 is the value of Kb at equilibrium. I multiply the concentrations of my products, so X squared, and then divide that by the concentration of my reactant. Now, we are definitely more than 1,000 times different here, so I can definitely reduce this or simplify it. So I'm just going to kind of ignore that X because that X is going to be so small, it's not going to make that much difference. So I multiply both sides by my denominator and get X squared is equal to 2.78 times 10 to the negative 11. Take the square root of that value and I get X equals 5.27 times 10 to the negative 6. Now that is, the units for that is a capital M. And what does the X represent? Well, this time the X does not represent H plus or hydronium. This time the X represents the concentration of hydroxide. Now you can take the log of this and find the pOH. That's okay. So the pOH is 5.28. The pH, which is oftentimes what you will be asked for, is 14 minus that value, or 8.72. So that's the pH at the equivalence point for this particular reaction. Well, what if we go past the equivalence point? Well, I still have my HA, and I'm still reacting it with strong base. So it's still going to make water and conjugate base. I still have 50 milliliters of 0.1 capital M molar. So I have 0.005 moles. This time I'm going past the equivalence point. So this time I'm just going to give it, why not, 55 milliliters of 0.10 capital M molar. So 55 milliliters in liters, 0.055, times the molarity, 0.1. 0.55 times the point, yeah, that makes more sense. Then I have 0.0055 moles of OH. Now the HA has become the limiting reactant. So I'm going to use all of the HA up, 0.005. Then I have an excess of OH. Now, although I do create an awful lot of conjugate base, it just doesn't matter anymore because the strong base is what's going to drive the pH. So now I have this excess of OH. I need to find its molarity so that I can find the pH. So I have 50 plus 55, or 0.05 plus 0.055. I have a total of 105 milliliters, which is liters is 0.105. So to find the molarity then, 0.0005, so that's 3 zeros and a 5, divided by 0.105, I have a molarity of 4.76 times 10 to the negative third. That is the concentration of my hydroxide ion. Now going back to the acid-base chapter, how do we find the pH from this? Well, you could calculate your hydronium ion concentration, or you could just find the pOH and then subtract it from 14. So the pOH, is 2.32. That means the pH, 14 minus the pOH, I get a pH of 677. So you could call it 11.68 or you could call it 11.7. I would prefer 11.7, but I'm not going to count you wrong if that's what you put. So we have several scenarios here where we have the pH of a solution before any base is added. We have added a little bit of base. Here we go. Here's before anything was added. All we had was that weak acid solution. And you worked those in the previous module. Then we added a little bit of strong base. And when we added a little bit of strong base, we saw how we were taking some of the moles of weak acid and making conjugate base. And then we could use the new ratio of conjugate base to weak acid in order to derive the pH. And we showed how going the long way, the way you're used to, and using the shorter way, the Henderson-Hasselbach, would lead to equivalent results. Now, the Henderson-Hasselbach is only valid before the equivalence point. And then we have, let's see, we got to the half equivalence point. The half equivalence point is where the pH equals the pKa. It's an experimental way to actually determine pKa of an unknown acid. And then we went to the equivalence point. At the equivalence point, the pH is going to be dependent on the concentration of the A- of the conjugate base. And we have to calculate the Kb from the Kw and Ka in order to find that pH. And then past the equivalence point, our pH is only going to be dependent on the concentration of the excess hydroxide ion.